Okay, now we're going to focus on Chapter 7, the intermolecular forces and the phases of matter. So do you ever wonder what keeps the ice molecules together and the truck on the surface of the ice? Unfortunately, this truck was not so lucky, but we oftentimes do see people, ATVs, ice fishermen, people driving cars on the ice. How is it that ice is so strong that it can hold people and things on top of it? So for this chapter, we're going to look at how those intermolecular attractions are working to create such strong bonds to be able to do this. First, we're going to review the phases of matter. A solid is the most condensed phase of matter, as shown in the dry ice in the picture below. Liquid is somewhere between a solid and a gas, like the water we drink every day, and gas is the least condensed phase of matter. A lot of times we can't see it, but as you can see, we have liquid oxygen here and liquid nitrogen, but when it turns into a gas, sometimes it can be seen, sometimes it can't, but that is the least condensed phase. So first, looking at gases. Separate molecules move very, very rapidly. The higher the temperature, the greater the motion. There's very little interaction between the molecules. As you can see from this picture, hot air molecules move very fast and are very far apart, and the cold air molecules move slowly and are much closer together. In the condensed phases, such as solids and liquids, they're held together by intermolecular forces as shown between these water molecules here. Energy is required to break those apart. For example, in order to melt ice, we have to add heat to it. When you take your ice cubes out of the freezer and you bring them out to the kitchen, they're going to melt because you're adding the heat energy of the surrounding kitchen air to it. So the relationship between the energy and the phase of matter. As energy lowers, interactions become greater as a result of the molecules slowing down. So as you can see from these water molecules here, as the water vapor is cooled, kind of like that cold can of soda on a hot summer day, they're pulled closer together. As they start to cling together, they form this new liquid called water, or the condensation that grows on the side of that cold can of soda. So as I just described, that condensation is the transition from a gas to a liquid. The opposite is vaporization. That is going from a liquid to a gas. For example, when you put your pan of water on the stove and you turn it on, you can start to see the water vaporize out of the pan. So which phase transition involves the addition of energy, condensation or vaporization? The process of vaporization involves the addition of energy because the molecular forces must be overcome. As you can see, we have a liquid. We added the energy of the heat on the stove to turn it into a gas. Just like we had the ice cubes in the freezer, brought it out to the warm kitchen, the heat of the kitchen caused it to turn to a liquid. So this brings us to boiling point. This is the maximum temperature to which a liquid can be heated. It's the temperature at which condensation and vaporization occur. This is defined by the strength of those intermolecular forces. If we look at the molecular view of a liquid, the molecules are tightly packed together and don't move much. But when the kinetic energy is greater than the forces holding those molecules together, by adding the heat, turning on the stove, those molecules begin to break free. I found this little interesting picture below here. With evaporation, and did you ever notice that when water starts to boil, you start to get the bubbles in the bottom of the pan? This is why. Well, first it'll evaporate. There's no bubbles, but we still have some evaporation. The bubbles cannot form since the vapor pressure is less than that atmospheric pressure. But when it starts boiling, bubbles can form and rise since the vapor pressure can overcome the atmospheric pressure. I thought that was kind of neat. Then we have going from a liquid to a solid. This is the polar opposite. We're now at freezing point. Further cooling will reduce the motion of those molecules. We still see very, very small vibrations of those molecules, but because they're moving so slowly, they maintain a solid. I thought this was really interesting. So we're looking at 1 billion degrees of separation. That's kind of just a term that it's using for this picture, but there certainly isn't 1 billion degrees. We take the temperature of the universe from absolute cold to absolute hot. The absolute coldest possible temperature is negative 273.15 degrees Celsius. This is 0 Kelvin. When you look at Uranus, okay, minus 216 degrees Celsius, that's the coldest planet in the solar system. That is minus 350 degrees Fahrenheit. It is almost impossible to wrap your head around. Even colder than that is the Boomerang Nebula, which is 5,000 light years away. That is negative 272 degrees Celsius. So we're achieving absolute zero. With absolute zero, when we get that cold, there's absolutely no molecular movement at all. So even though our ice cubes in our freezer are minus, I don't know, what would it be Celsius? Fahrenheit, it's probably around 0 Celsius, a little bit lower than that. In that ice cube, if you leave that ice cube in there long enough, it's going to disappear because it still has molecular movement present. So you notice your ice cubes in the tray, first they start off nice and crisp and square, and then after a while they start to get some rounded edges, and they actually start to taste bad too, but they really start to get smaller because there's still evaporization happening because we're not at absolute zero. Going to the opposite end, we're looking at elements like helium and oxygen and the boiling point of helium and the melting point of helium. They are extremely warm. So it's interesting to see this huge spectrum of temperatures and how cold it can absolutely get. So when we look at an overview of these three phases, we can look at a few things. The transitions and properties can be explained by looking at the kinetic energy that they have, or the motion, and the intermolecular forces of the molecules to stick together. The stronger the force, the more the molecules are attracted to each other. And phase transitions occur as a result of competition between those factors. So let's think about this. The boiling points of ethanol and water are 78 degrees Celsius and 100 degrees Celsius respectively. What can be said about the strength of the intermolecular forces of each? Well, due to the higher energy needed to overcome the attractions in water, we can conclude that the interactions are stronger in water than ethanol. So if you had ethanol sitting out and water sitting out, the ethanol would evaporate much faster. Try drawing a picture showing the interactions between hydrogen and chlorine molecules. Use a dotted line to represent those intermolecular forces. As we can see, other arrangements of intermolecular forces are possible. Just make sure that the positive end of the molecule approaches the negative end of another molecule. Again, it's like that magnetic force. You take the positive end of a magnet and the negative end of another, and they will stick together. That's how molecules stick together as well. Some of the types of intermolecular forces include London forces. These are also known as dispersion forces. You're going to have to be responsible for the definition of this guy. They are weak forces caused by the shifting of electrons. They're present in all molecules, and they're individually weak but become important in very large molecules. London forces are over several molecules, as you can see here. The very positive charge repels electrons in the molecule to the left. And the negative charge repels electrons in the molecule to the left, and the positive charge attracts electrons in the molecule to the right. So why are intermolecular forces between water molecules much stronger than those found in oxygen? Water is a polar molecule containing permanent dipole-dipole interactions along with these London forces. O2 only exhibits London forces as a result of the temporary motion of those electrons. So which of the following do you think would experience a stronger London force? Methane or hydrogen? The CH4 would exhibit stronger London forces as a result of the increased number of electrons present in the CH4. Next, we'll talk about hydrogen bonding. This is a very strong type of intermolecular force. Interaction between a polar oxygen, nitrogen, or fluorine atom and a polar hydrogen on a neighboring molecule. Here are some of the effects of that hydrogen bonding. In water, the boiling point is 100 degrees Celsius. The mass would indicate a lower melting point than that of acetone. Acetone does not hydrogen bond, and it boils at 56 degrees Celsius. One would expect a higher melting point because of a higher mass. And you can see those two molecules below. Remember that intermolecular bonds are much stronger than intermolecular interactions. For example, it takes 400 kilojoules of energy to break 1 mole of oxygen-hydrogen covalent bonds, but only 16 kilojoules to break 1 mole of hydrogen bonds. So intramolecular attractions are much stronger than intermolecular attractions. Which of the following compounds has a melting point of 35, and which one would have a melting point of 78? The second compound would exhibit the higher melting point, as it can hydrogen bond to itself. More energy would be required to break those interactions apart. So hydrogen bonding can be found in DNA. Hydrogen bonding holds the two strands of DNA together. It allows for easy separation. So next we're going to look at the difference between molecular and non-molecular solids. A molecular solid is held together by intermolecular forces. It contains very discrete molecules, and it's usually formed between group 1A or group 2A metals and a nonmetal. Examples would be something like water or candle wax. Much lower melting point, right? A non-molecular solid is held together by very strong covalent or ionic bonds. They've got long gauge lattices like the salt molecule over here. They exhibit a much higher melting point and include examples like salt and diamonds. While you can put salt in water and it will dissolve, trying to get salt to melt on its own requires a very, very high temperature. We also have network solids. These are also called network covalent substances. Large networks of atoms are held together by covalent bonds. Examples of this are diamonds and glass. Very difficult to melt. Then we have metallic bonds. This is sharing of electrons like the covalent bonds. Electrons are free to move between the nuclei. We see melting points of over 1,000 degrees. Here's how we can classify solids by type. Those molecular solids are held together by weak interpolar, dipole-dipole forces, London forces, and hydrogen bonds, low melting points. The non-molecular solids have chemical bonds like ionic, covalent, and metallic, very high melting points. Take a minute to classify the following as molecular, ionic, network, or metallic solids. Pause here, take your best guess, and hit play to see the answers. Zirconium has a melting point of 1,852 degrees Celsius. It is metallic. Lead is 328 degrees Celsius. It's metallic. Calcium nitride is ionic. Graphite form of carbon is network. It sublimes at 3,652 degrees Celsius. And then we have yellow phosphorus. This is just a molecular. It is melting point of only 44 degrees. So next we'll take a look at antibiotics and how hydrogen bonding is involved with them. Specifically vancomycin. And if you're familiar at all with antibiotic resistance, this becomes very interesting as it brings it to a chemistry molecular level. Antibiotics are used in the treatment and prevention of many diseases, especially gram-negative bacteria. And we've learned over time that the overuse of antibiotics has accelerated the growth of antibiotic-resistant bacteria. So people are told by their physician to take their antibiotics, and they feel better, so they stop taking them. This can have a very detrimental effect as we see survival of the fittest with the bacteria that make it through. And I'll show you here how that happens. So specifically, we're going to look at vancomycin. This is a very, very potent antibiotic that's saved for only extreme cases of bacterial infection in humans. This antibiotic hinders the growth of the bacterial cell walls, which kill the cells. Looking at the bottom of this picture, the black compound is a glycopeptide. It's part of the newly forming bacterial wall. See, there's an NH3 here and more NH, oxygen, hydrogen. There's all types of bonds down here. And the vancomycin comes in and stops the formation of this cell wall, killing the bacteria. So you can see these hydrogen bonds here. This vancomycin-resistant bacteria has become very common since the 1990s. So what happened is the cell will start to replace a single NH with an oxygen, decreasing the effectiveness of vancomycin 1,000-fold. Okay, so it takes the NH and it turns it into an oxygen. This makes the hydrogen bonding very challenging. So how does antibiotic resistance occur over time? Well, if you have a high number of bacteria, a few of them are resistant to antibiotics. Antibiotics will kill the bacteria that cause the illness as well as good bacteria in the body. The strongest will survive. The resistant bacteria now have preferred conditions to take over. Those resistant bacteria that are stronger now reproduce, creating even stronger bacteria and more resistant bacteria, causing more problems, making it more difficult to destroy. So what they're coming up with are replacement antibiotics. Drug companies are trying to develop replacements that can add a nonpolar tail to anchor to the cell. So this could cause that to work more effectively moving forward.